Welcome back. In this section, we'll be looking at exponential modeling and just some further exploration of exponential graphs. Alright, so it's essential to understand what's happening in an exponential model. So each graph will help us greatly. So the values of intercept in particular. Starters, I always ask my students to analyze and plot these graphs on X and Y axis. So what is the purpose of this is that you realize how does the model behave at time zero, and what is the of the model when time reaches some large value. So for exploring how this model will act with respect to time, we we can rewrite this function here, whatever this p value of p is an exponential function is. We can put the to the power negative 0.6t in the denominator there. Right, so when t gets to a large value, this value of t approaches a large value, we are going to be dividing with 160 by a huge number, and that basically means that it's its ultimate value when t is very large is going to be this fraction will approach zero when t is very large. Okay, so what we end up with is with the value of 20. Now that 20 is an indication of the asymptote of the graph. All right, so this exponential model, what's the value of p when time is zero? At time zero, we will have a 20 plus 160 times 1, because e to the power of 0 is 1. Okay, so this the initial intercept of the graph will be 180, somewhere up there. Now, will the graph have a positive intercept or negative intercept? Because of the minus sign here, it it will have a shape like so. It will have a exponential decay form. Now there is uh, this asymptote where the graph will approach. This is what we found it to be actually. This 20 that we calculated is the ultimate value of the graph, or rather the asymptote of the graph. E will approach 20. Okay, value of y will never fall below 20, because we are essentially just adding a 20 to this exponential function here. So that's important, that we found this intercept to be 180, and we know that ultimately we can draw a horizontal line here parallel to the x-axis and indicate that this the model will be an exponential decay where large values of t actually rather than x will take us there. So I hope this is a further explanation of how to draw graphs for some functions like that. So I'm gonna rub off my writing here and plot it nice and neatly like so. And I showed you how to calculate the intercept there and this value of uh, the asymptote. Alright, horizontal asymptote. What about this next graph here? What's the limit of that function when t approaches in? So this is not part essentially not part of the practice that your book makes you do, but if you understand what's happening here, you understand how to draw the asymptote for the graph, and I think it will make your life a little easier. So what happens is that here we can rewrite this as the denominator e to the power of positive 0.6t, and change because I'm taking that negative sign away in the denominator. So then for large values of t, again, we are dividing 16 by a huge number here, and therefore this fraction will become 0, and this graph will also have a horizontal asymptote of y equals to 20, but the shape of this graph is kind of different because of this minus sign. actually I'm going to have to draw my asymptote further up there actually, so that I can show you when t equals to, so let me rub this off. uh, when the y equals to 20 is up there, and why do I put it up there rather than down here? Because if we evaluate this function and find at point t equal to 0, p will be 20 minus 16 times 1, and that, what is 20 minus 16 is 4. So it has a y-intercept of 4 here, alright, and actually what's going on is that it will approach y equals to 20 in a reflective shape like so. Why? Because of this minus 16 that's multiplied with that negative power. The negative power and this negative at the front literally take the exponential curve that goes like that. They flip it in x and y axis. So flipping it in y axis, and then in x axis we'll take it, so we'll have two transformations here, and this shape is added 20 to it. So then final transformation, this is a reflection of the graph down here, and then we'll move it up by 20 units, okay, and to the right, because this because of the numbers here, in the shape of the graph will be like so with intercept of 4. All right, so if I rub this off and show you the a more professional drawing, will look something like so. Alright, you can test this and plot it with your graphic calculator. It should help you understand how I got the asymptote. This is I calculated the asymptote by taking a large value for t and substituting it into the function basically. So it should help you understand it a little better. So again, this is started question is asking us to calculate the shape of the graph on top of the page for y equals to 2 plus 160 times e to the power of that. So you can rewrite that function as 160 over e to the power of 0.6t, and take the limit as t goes to a large value. This will approach, the fraction will approach 0, therefore the y will have, it will have a asymptote of equals to 2, asymptote equals to y equal to 2. And what is the initial value of the function when t is 0? You say y equals to 2 plus 160 times e to the power of 0, which is 1 here. So this means that 1 times 660, and add 2 to that, 162. So the intercept is 162. The negative sign in front of the t and the coefficient there is telling me that it's actually going to be some sort of shape like so, where you have x-axis here, y equals to 2 here, and it has a negative gradient because of that. So these are the shift, we shifted the value of the graph up by 2, and also the scale factor of 160 there. Alright, so the plus sign in front of 160 means that it will have some sort of a shape like so. So it will ultimately look like this. Alright, so in part question 2 here, I'm just again introducing you to some exponential models, and where you solved the problem like this before when we explored bacterial number, population of bacterial. Here is a house value. It was worth 1 million on 1st of January of year 2000, and in 2 years, exactly 2 years after that, it's worth 1.2 million, assuming a constant percentage change here in this question. Work out what's the annual percentage change growth. So you pause the video, have a go at it. It's similar to the question I've done before for you, so I'll, I'll talk less this time. You're assuming at the year 2000 to be year zero here. So the year 2000 is where t equals to 0, okay? So don't confuse the value of 2000. So when you get to year 2002, t equals to 2. So we are substituting that for this exponent here. So basically, value of a here is multiplied by 1, and A is basically 1 million. I've dropped the 10 to the power 6's here because they are going to make a difference when we divide these two equations by each other to find the value of. So values of A will cancel away, and the ratio is the important part. So I took the second equation and divide by the first equation here. So this is equation 2 divided by equation 1. Alright, so then we get 1 plus x squared, so is 1.2. We're going to take the square root of both sides, and 1 plus x is this value here, and we can subtract 1 and turn it into decimal, or rather a percentage, from a decimal into percentage. Alright, so that's answered part A for you. Annual percentage change is 9.5%. Now, if the same annual percentage change was applicable over the next 10 years, what will it be in 2010? Alright, so you substitute this value back for x into the model, and you, rather than using power of 2, you're going to use power of 10, and you are going to use the value of a that you found here to be 1 million. So you end up with this. This is the value of a as 1 million. I've written it, well, I didn't write the 10 to the power 6 here, but that's assumed that we're working in millions here. So I've written the answer as 2.488, and I put million there instead of writing 10 to the power 6. So that's that, and got this model of pesticides now to look at. The city of pesticides in a section of a field is modeled by this exponential function here, where you will have at time 0. I can substitute 0 in this expression and see that it will have intercept of 160. So it makes life a little easier just to, if you read the question, it says that estimated density of pesticide after 15 days. So t is the time in days, okay? So you substitute the value of 15 into this expression to answer part A. Alright, so to answer part A, we just substitute a value and evaluate it to be 146.2. Now, part B is saying interpret the meaning of 160 in this model. So at time t, if you realize that 160 is when p is 160 when t is 0, e to the power of negative 0.006 times 0 is still 1 here, and that's the initial value of the pesticide at the beginning of the time, or in initial value of time, the pesticide in the model. Okay, so then we are going to look at no time has passed since the model started, no amount of pesticides sprayed in the air. Okay, so then part is asking us to differentiate this exponential function with respect to time and interpret the significance of sign of this answer. So to differentiate, if you remember a couple of exercises I showed you, you bring the power of e down multiplied by the coefficient at the front, but you don't take and change e to the power of minus 0.006t. You leave the power alone as it is. Alright, so those are the next few parts of the question. We're not concerned about them yet. So multiplying the coefficients with each other, we'll end up with this number here, and the sign is negative. What does this tell us? So part D is saying interpret the significance of this sign. So well, this sign is just saying that the graph, if you remember, the graph of e to the power of negative 0.006 t is something like so. We will have, no, sorry, it's the exponent, original exponential is like so. So it will, this number at the front will, if this was e to the power of positive, if this is a positive t here, it will reflect it down like so. And then the value in front of t is negative, so it will reflect this graph left to right. So we will have a graph that will be actually upward sloping rather than downward sloping because of this value. So this is just saying the rate is falling though. Okay, it is changing, it is increasing, but at a slower rate. Okay, the negative sign is saying that it's changing it's increasing at a slower rate. Okay, so this means that the function in this case is downward sloping, the gradient is negative. Okay, so the the rate of change is this. So the original function is increasing. It has this kind of a shape where the intercept is there, but the grade this is a different function altogether. All right, so the original function looks something like that. The graph has intercept of 160 and it's downward sloping, and actually the uh, y asymptote, the horizontal asymptote is actually going to be, if you substitute a large value of t into this function here, this is exactly the same function written as a fraction. So taking a limit of t going towards a large number will actually ta- make it go towards zero, because you're not you don't have anything added here. 160 divided by a very large number still has a y asymptote uh, close to y. At the horizontal asymptote is y equals to zero. It's this line here. It's literally the x-axis. So it has a negative gradient, and the is telling us that the negative sign is telling us is that basically the function is downward sloping. The gradient is negative. The context in this context means that the level of decay of the pesticide is decreasing. Okay, it is downward sloping, but it's falling at a decreasing rate. Actually, if you do graph this view, this was the graph for that, which actually I have it down here. The original function looks like so, and okay, I just answered next part for you as well, where it says what is the horizontal asymptote of the function. I just proved that it will approach zero. So there, and what if you graph the derivative function? Actually, it will look something like it has two reflections, one of the exponential function. First, this function it will reflect in y-axis because the negative in front of t, so it will look something like so. And then this reflection will reflect it down here. It is actually something like that, and why it's increasing but at a slower rate. Okay, the rate is falling. Okay, the rate is negative and falling. Y value here is negative, but uh, it's falling at like a less negative value for the further forward we're going. So then finally, what was I've added this part G. It says what's the daily percentage change. All right. So this is a challenge question for you. You want to turn this change of 0. e to the power of negative raised to the power t. T stands for the day, right? So this number you can change it to like a base. This is like a natural number that you can write it as 0.994. And what does that mean? If you think this is a multiplier, right? 1 plus x is this number. That's a multiplier, so x is a negative value, has a negative value, and that is like 0.6%. That's less than 1%. All right, percentage. If you think of it, is like negative 6/1,000. Actually, that's why it's 0.6%. All right. So that's that, and I believe that's the last question for this exercise. These are somewhat you do have to understand what happened with the graphs there. So I'll see you in the next video.